Before we get into periodic motion, and in particular simple harmonic motion, let's review the motions that we've talked about so far this year. We began a long time ago talking about different ways to get from A to B, and the first one we talked about was translational motion. And that would be a situation where you're basically in one dimension, two dimension, or three dimension. An object is at position A, and then later on we find it at B. So this would be an example of two-dimensional motion. This would be one-dimensional motion. Then we talked about projectile motion. Now projectile motion is also translational motion, but it's a special case. Now why is that a special case? Let's see, where's red? And the reason it's a special case is because projectile motion is free fall motion. And I'm trying to get my colors down here. I'm going to try to do forces in blue. Let's see how long that goes. And basically projectile motion is translational motion when the only force acting on the object is gravity. And of course we only looked at the limited case where you have some initial x velocity. The y velocity is 0. The initial y velocity is 0. And then it falls. Okay, so that's projectile motion. A recent motion that we looked at was circular motion, and we looked at, in particular, ours was uniform circular motion. Okay, the uniform just means constant speed. And one of the big points about that, obviously we're not going to go into too much detail here, is that circular motion results when you have a inward directed force. Now the direction of the force is always changing, but for uniform circular motion this inward directed force is constant. I just put a C there. Well, I'm going to put C's everywhere because that is for centripetal. And remember, centripetal center seeking. Okay, these are the motions that we've talked about, and now we're going to talk about a new one. And now, drum roll, that motion we're going to talk about is, well, in the general term, in the most general case, we're going to talk about periodic motion. And obviously that word periodic means a lot, but we're going to go beyond that because we're going to look at a special case of periodic motion, which is oscillatory motion. And we're going to go beyond that. We're going to look at a special case of oscillatory motion that's called simple harmonic motion. So, and obviously we're going to get into what exactly is simple harmonic motion. Periodic motion would be anything that anything repeats itself over time. You could be deciding I want to walk this way, and then you walk for 30 seconds, and then you go back and you arrive back, and then you just repeat the cycle over and over again. Oscillatory motion could be, well, okay, what makes oscillatory motion is you don't really have a restoring force. So the key thing about oscillatory motion is it requires or results when you have a restoring force. More on that later. But we can't really say that you have a restoring force that forces you to go back and forth here. It's kind of a conscious choice on your part. But it would still be periodic motion because you're cycling through this motion. You leave from A, and then you go to B, and then you return back to A in some periodic fashion. Oscillatory motion is back and forth motion that results when you have a force that compels or makes that motion. And simple harmonic motion, well, okay, I'm getting ahead of myself, requires a linear restoring force. More on that later. Okay, so let's talk about some key terms for periodic motion. Key features, key terms, what have you. And this is for all periodic motion. This could be you walking back and forth, making a conscious decision to turn around, or it could be our spring mass oscillator. Obviously, the term periodic, and even this would apply to circular motion, as we've seen. Periodic motion must have a period, and we are familiar with this from orbits and circular motion in general. I have been very good this year about using the Greek, I don't know what you call this, it's probably not T in Greek, but anyway, I've been putting these little corners on my T, but generally you often just see it just as a capital T. And we know what this is. This is the time per cycle, the time it takes to go around once. And it has my units. Let's see, I'm going to make green is going to be my unit. So it has units of time, and generally we're going to say seconds, although of course it could be any unit of time. Another key term in any kind of periodic motion is frequency, abbreviated almost always as an italicized F, but really any lowercase f will do, but I do italicize. This is the cycles per time, and it has units of, you could say cycles, I'll go ahead and write it, you could say cycles per second, but oftentimes we just see that written as per second, which you can think of that as 1/2, which is a kind of strange unit. Strange looking, but that's what it is, cycles per second. Okay, so now is there a relationship between the two, period and frequency? And I think the answer would be yes. And all we have to do is look at the units for period is seconds or per time, and the units for frequency is 1/2, really, per time. And so of course we're going to see that if we have the period, we find that the frequency is just 1. Why am I writing that? Let's just skip that. Let's go period is equal to 1/2 the frequency, and the frequency is equal to 1/2 the period, or the inverse. So they are the inverse of each other. Time for some practice problems. Let's use, I don't know, orange. Okay, suppose that we have a period of some periodic motion is, let's see, let's make it pretty fast. Let's say it takes 0.10 seconds to do one cycle. What would the frequency be? Well, what we look down here, we see that they are the inverse of each other, and so the frequency is going to be the inverse of whatever the period is. In this case, it's going to be the inverse of, well, 1/0.10 seconds, and that becomes 1 divided by 0.1 is 10, and this is per seconds, or we could write that as 1/1 second, but or I guess we could say, we could also write it really more realistically, 10 cycles per second, but we're not going to see it written that way. You're going to see it written as 10 hertz, because the unit of per second is called, or has been named in the hertz in honor of Heinrich Hertz, who was the first person to artificially create radio waves, which is pretty cool. And it's abbreviated as H, capital H, lowercase z. Let's do another one. I'm forgetting the orange. Let's go to green. Let's do another one. Let's go the other way. We'll say, suppose that the frequency is 1000 hertz. What is the period? Again, it's just a simple case of, to get the period, you do the inverse of the frequency. This is 1/1000 hertz, and 1/1000, I think that's 0.001, I hope. And the inverse of 1/hertz basically is seconds. So it takes only 0.1/1000th of a second to for that periodic motion to complete one cycle.